So welcome everybody after the tea break in this last session this afternoon. This last session is also about biological processes in water treatment, and in this session we focus a little bit more on the nutrients, the phosphate, the phosphorus, nitrogen and sulfur compounds are the focus of this session. First speaker is Christel Kampman, and she's a PhD researcher at Wageningen University, and she works on the project Denitrification with dissolved methane from anaerobic digestion, a novel opportunity for sewage treatment. And I think that's also the topic of your presentation.
Thank you for the introduction. In this presentation, I would like to tell you about denitrification with dissolved methane specifically. And we think this could be a novel opportunity for wastewater treatment. The research I will present in this presentation is performed at the Subdepartment of Environmental Technology of Wageningen University. And in this project, we cooperate with the Department of Microbiology from the Radboud University Nijmegen. And also you will find some of their employees among the authors. In the project, we research amongst some other processes denitrification coupled to anaerobic methane oxidation. This is a process that is performed by a novel bacterium which has been named Candidatus methylomirabilis oxifera. And it was first described in 2006. Then our project partners from Nijmegen were able to enrich the bacterium from sediment from the Twente Canal in the Netherlands. And the bacterium converts methane and nitrite to carbon dioxide and nitrogen according to the equation you see on the screen. And for the bacterium lives in anaerobic conditions, and research so far indicates that it cannot cope with oxygen very well. It performs a unique intra-aerobic pathway. And the pathway is shown in this figure. This all occurs within one bacterium. It converts nitrite to nitric oxide, and then to oxygen and nitrogen. And subsequently it uses the oxygen for the conventional aerobic methane oxidation. And we believe that because the bacterium converts both nitrogen and methane, it offers opportunities for the treatment of effluent from anaerobic wastewater treatment at low temperatures, which I will elaborate further on in this presentation. And something to remember, from now on I will use the, I will use the abbreviation DAMO for this process. Well, the background of this project is that we would like to apply anaerobic wastewater treatment at low temperature. And by low temperature we mean Dutch conditions. So that is a winter temperature of 10 degrees Celsius and a summer temperature of 20 degrees Celsius. Well, we would like to apply anaerobic wastewater treatment because it has many advantages over the conventional aerobic activated sludge treatment that is currently applied. Examples of advantages are that it has a smaller footprint, that it has lower costs, it produces less biosolids, so less sludge that has to be disposed, and less carbon dioxide emissions because instead of oxidizing all the organic matter from the wastewater to carbon dioxide, it produces methane. And also the system has a lower energy consumption because no aeration is required. In fact, it even produces energy as methane. However, the effluent still contains some compounds that have to be removed, and those have probably delayed the application of anaerobic wastewater treatment at low temperatures. And most important are that no nitrogen is removed and that the effluent contains dissolved methane. In this case, nitrogen cannot be removed via the conventional nitrification, denitrification pathway because in the anaerobic sewage treatment, the readily available organic carbon sources that are required for denitrification have been used already. So methanol would have to be added or something like that, and it's not really attractive. And methane is dissolved in the effluent. Here you see a number for 10 degrees Celsius, then 20 to 30 milligrams per liter of methane is dissolved. And this is a really strong greenhouse gas, so it should be removed. But if you remember the equation I showed on the first screen, and I repeat it for you here, this bacterium can convert methane and nitrite in one process. So it could solve the two major problems associated with the effluent from anaerobic sewage treatment at low temperatures. And therefore, we think that DAMO is really applicable for the treatment of effluent from anaerobic wastewater treatment at low temperatures. And we would like to apply this DAMO system in a new concept for anaerobic wastewater treatment, which is shown here. We propose to remove the organic matter by a combination of a UASB reactor and a sludge digester. This is a system that has been successfully applied on pilot scale by several researchers already. And the idea is that you design a UASB reactor for summer conditions, so quite small, and in this you treat the incoming wastewater at ambient temperatures. Soluble COD is removed in this reactor, and suspended COD is entrapped. And the suspended COD and also sludge is transferred to a digester, which is operated at elevated temperatures. And this is feasible because it only is a small stream relative to the total influent. And in the digester, hydrolysis takes place and methanogens are grown, which are then transferred back to the UASB reactor. The effluent from the UASB reactor contains dissolved methane and ammonium. And in order to be able to remove this by the Downhill process, an additional nitritation reactor is required. So from this nitritation reactor, nitrite is recirculated, and together with methane, this can be converted to nitrogen and carbon dioxide. And in this presentation, now I would like to focus on this small part of denitrification coupled to anaerobic methane oxidation. And I'd like to start with an overview of the research that was published when we started our research. There were 3 cultures. One was the enrichment from the Twente Canal sediment that I discussed earlier. Another was a continuation of this enrichment. And the other was an enrichment from another sediment from the Netherlands, from the Ooipolder. What you can see from this table is that it takes a long time before the activity first occurs. And this is because the bacterium has a doubling time of about 2 months. And therefore, we think that the choice for sequencing fed batch reactors and completely stirred tank reactors, which don't have complete biomass retention, is not the obvious choice. Also, the reactors are operated at relatively high temperatures if you want to, you don't want to apply these temperatures for wastewater treatment. Also I have to point out that the highest activity so far was 36 milligrams of nitrite N per liter per day. So this has to be increased at least 5 times before it can compete with conventional denitrification. What I did is I tried to enrich the bacteria using a membrane bioreactor with complete biomass retention, because of this low growth rate. And I inoculated this reactor with a mixture of sludge from a municipal wastewater treatment plant. And we used this inoculum because this is a widely available and on-site available source of inoculum. However, after 14 months, to boost activity, I spiked it with bacteria from another enrichment with this Ooipolder sediment. And to be closer to the conditions that are actually applied in wastewater treatment, I operated the reactor at 20 degrees Celsius, and I fed it with medium which contains, besides nitrite and nitrate, also effluent from a municipal wastewater treatment plant. And methane was supplied in excess at all times, and it also was used for mixing and also for cleaning the membrane. Over the course of the enrichment, I have followed the nitrite consumption rate of the reactor. I did some batch experiments in which I compared the consumption rate of methane and nitrite to determine if the ratio was according to the stoichiometry that I've shown before. And also because the growth rate is so slow, molecular tools for detection of the right bacteria were really important. And in the next couple of slides I will discuss some of these results. The next figure shows the nitrite consumption rate in time, so time on the x-axis and the nitrite consumption rate on the y-axis. And well, I divided this reactor into 4 zones. In the first zone, indicated by the Roman numeral on top, well, hardly anything happened. So this was really a startup time in which heterotrophic denitrification appeared, and slowly the right bacteria have grown into the system. And during the following 120 days in zone 2, there was an increase in activity which resulted from just from the bacteria that were present in the sludge and that we enriched in the system. Then in the third zone, this is the period where I added the bacteria from another reactor, and the activity increased more. Results I did not show, but that I obtained, is that in a reactor to which this that was not spiked with these bacteria, you don't see such a sharp increase. Well, unfortunately, after 600 days, the consumption rate stagnated at, well, also 36 milligrams of nitrogen per liter per day. And so far, we have not been able to exceed this value. And it's quite remarkable that this stagnation was also observed by other researchers. Initially, we thought this maybe was caused by biomass washout, but in the case of our system, this can really be excluded. We have ultrafiltration membranes, and the bacteria can never make their way out. So maybe it is because of product inhibition, or because some growth factors are missing. And at the moment, we're attempting to increase the consumption rates by changing the medium composition, however, not successful so far. Well, as you might have noticed in the previous graph, it took a really long time before activity got started, and therefore the molecular analysis were really important to detect the growth at an early stage. So first I did a polymerase chain reaction, PCR. And the idea is that you amplify DNA of this target organism, and then you see some bands appearing like this, and then you can see if they are there. It's not qualitative, but here you see a positive control of, we did both a direct PCR and a nested PCR. In the direct PCR, first a large part of the in the direct PCR, directly we targeted this candidatus methylomerablis oxyphera. In the nested PCR, first we amplified a larger part of the RNA, and then did the amplification for the candidatus methylomerablis oxyphera. And at the place of the positive control, a band should appear in case the bacteria are present. And what you see is that, well, they cannot be detected by the direct method, and also in the inoculum, which was a mixture of those 3 sludges, you cannot see them. But after, how much is it, about 4 months of enrichment, you can see them in the reactors. So we don't know how much there are really, but it is an indication that they are there. And this was really important because only 6 months later, we could see an increase in activity. Well, with the PCR products, we made clone libraries, and we analyzed the sequences. And this shows that the bacteria that were enriched in this research are similar to sequences found in sediment, sequences that were found in a selection of Dutch municipal wastewater treatment plants, and also sequences from another enrichment from both inoculum and enrichment from an industrial wastewater treatment plant. Yeah, so despite the other reactor setup and the other inoculum source, the same bacterium appears. But both PCR and these clone libraries don't really tell anything about the abundance of the bacterium. Therefore, I did fluorescence in situ hybridization. What do I do wrong? There it is. And these two pictures show on the left the inoculum. So what you would like to see in the case of presence of the Dama-bacteria is, it's quite dark for you, I guess, is well, some dots appearing. Here it is all a blur, which indicates that these bacteria are not really present. So, and also after 6 months, the picture was quite similar, but after 12 months, yeah, they were clearly present. So it should be an equal sign. It says smaller than, but then there was 60 to 70% of Dama-bacteria in this reactor. And yeah, it has remained like that ever since. So yeah, summarizing, we were able to successfully enrich bacteria of the type Candidatus methylum oxifera in the membrane bioreactor, which was a new setup, at 20 degrees Celsius, which is lower than before, from sludge from a municipal wastewater treatment plant, fed with medium containing effluent from wastewater treatment. And together this indicates that it is a promising technique for the treatment of effluent from anaerobic wastewater treatment at low temperatures. However, the volumetric nitrite consumption rate is 36 milligrams nitrite N per liter per day, similar to the Oipolder enrichment. And at a typical influent concentration of 50 milligrams of nitrogen per liter, this would translate to hydraulic retention time of 1.4 days. And yeah, this has to be increased by at least 5 times to be able to compete with the conventional denitrification. And when I compare my results with results from other research, there's an overview table with on top, again, the 3 enrichments that I showed in the introduction. In the meanwhile, more enrichments were performed. They're shown here. And at the bottom, my enrichment. Well, this shows that despite a low growth rate, we were the only ones that decided to use a membrane bioreactor. And no, the temperature is still one of the lowest. However, the idea was using a membrane bioreactor would decrease the startup time, but it was 10 months, which is actually quite long. But the good thing is that despite the low temperature, we were able to reach an equal nitrite consumption rate as the Oipolder sediment reactor. So again, summarizing it, yeah, this appeared to be a successful enrichment strategy using a membrane bioreactor, sludge from wastewater treatment, and also 20 degrees Celsius. Maximum conversion rates of one previous research were matched despite the lower temperature. And yeah, we really believe that if conversion rates are increased about 5 times, this process could be applied for the treatment of effluent from anaerobic sewage treatment at low temperatures. So if this increase can be achieved, maybe in future, instead of having the conventional aerobic activated sludge system, we will use well, this reactor concept for anaerobic wastewater treatment at low temperatures. So I hope I was able to interest you for this new exciting process, and I would like to thank you for your attention.
Okay, thank you very much. Discussion we will have afterwards, after the 4 presentations.